A curve is a set of points in R3, but a path or a parameterization is a function that describes how you should move along the points in a curve. When you see R of t, this tells you the position after having moved for amount of time t. Now, for a given curve, there are infinitely many different paths possible. So as a simple example, let's take a unit circle. We've already discussed that one parameterization of this curve could be cos t sine t, but another one could be cos of 2t and sine of 2t. Now, the only difference here is that you are moving along the points on the curve at a different speed. We would only need half as much time to cover this. I could have picked any value for that period, and you could see that there are going to be infinitely many different parameterizations. This is something that we're going to call a re-parameterization of a curve. Given one path function like this, r of t, you could create a new path. You could take your original path and then input some other function on the inside. So you could think of this as the new parameter. Now, in the example above, we had this function as 2t, and the parameterization, let's say r of u, was cosine of u, sine of u. So I took r1, 2t, and that's how I got to the second parameterization. Now, the reason that I'm going through this is because if there are infinitely many different parameterizations for a curve, is there a best parameterization? Is there one that we should pick over the other ones? And best perhaps isn't quite the right word. We're going to talk about what is the most natural parameterization to use. And this is a discussion that's going to be related to arc length. So if I'm given a certain curve and I know that it has a smooth path on some interval a to b, and then it takes us to R3, remember that this initial point here is the vector r of a, and this final point here would be given by r of b, and in the middle we'd have some r of t. Well, the length of this curve is an integral from a to b, the magnitude of the derivative of that path. Now, this is a constant. It's a number. When I have this integral, the choice of integration variable is irrelevant. I could have used u's because these are all dummy variables in the same way that the t here is a dummy variable. Now, I'm introducing this idea of a new variable because now we're going to introduce what's called the arc length function. Now, the arc length function is closely related, and we're going to call this s of t. So if I give you a curve with a path that goes from a to b, and it takes us into 3 space, the initial point here, as before, is going to be r of a. Let's keep a variable point here. So this distance right here, this is going to take us to r of t. And now instead of having a length, which is a constant and fixed, we are now going to integrate from a to t, derivative magnitude. The u is a dummy variable, so it doesn't really matter what we choose. We just don't want to choose t, because this variable and this variable have to match. That's what makes it a function. And essentially, it's like taking a piece of string and measuring how long it is from the beginning of the curve to the point that I have there at the end. If I were to say s of a, the way that we've defined this, it would be an integral from a to a of this quantity. And you know by integral properties that anytime you have the same limit in your integration, the value must be 0. If I wanted to take the derivative of this function, it would be like saying take a time or a t derivative of this quantity. If you wanted to differentiate it, this comes from the fundamental theorem of calculus. And at the end of the day, this is going to give me the magnitude of that derivative function evaluated at t. Because this is a length, I know that this always has to be greater than or equal to 0. So I have a new notation for speed here. The speed we've already defined as the magnitude, but it could also be this function. And I know that it has to be greater than or equal to 0. Remember, it's always a scalar function. When I see s prime of t, this is the speed while moving along the curve C with this path. Here's the key idea. We are going to use arc length as the natural parameter for every curve that we deal with. And when I say natural, arc length is built into every curve. All curves have a length. Something that's intrinsic. And so it makes a lot of sense for you to say, if I'm going to start here, the parameter is going to be how far along the curve I've moved. And then when I talk about writing R of S, that means the position after having moved S units along the curve. And that's a little bit of a difference. When we had R of t before, it was the position after having moved for a certain amount of time. Well, when I do an arc length parameterization, the interpretation is the position after having moved this far along the curve. To try to illustrate this to you, I'm going to talk about the example from the previous video. We have a helix, and we were given this path sine of 2 pi t in the I, t in the j, and cosine of 2 pi t in the k. Now, for the arc length, we're going to start with t is 0 just as an arbitrary choice. So the arc length function along the helix would simply be this expression. From the previous video, we found that this quantity here was constant, 1 plus 4 pi squared du. So at the end of the day, this is going to give us now 1 plus 4 pi squared t. So I have a relationship. This tells me how to connect the old parameter to the new parameter. We can reorganize this for t and get s over 1 plus 4 pi squared. So now I'm going to re-parameterize the curve in terms of this arc length function. Wherever I saw a t, I'm going to replace it with this quantity. So I will have sine of 2 pi t. Well, now this is sine of 2 pi s, 1 plus 4 pi squared. That's in the I direction, plus s over 1 plus 4 pi squared in the j direction, and then I'll have a cosine of a 2 pi s over that square root in the k direction. So I have successfully re-parameterized this curve. The input variable is distance along the curve. You tell me how far I've walked along the curve, I will tell you where you are in R3 on the curve. So why do we care about arc length parameterization? Well, arc length is the natural way to talk about a curve. It has nothing to do with time or motion along the curve, but it also gives some insight into physical quantities. And I'm going to discuss this now. We've already talked about things like velocity and acceleration. If you introduce arc length, you get a whole new light on each of those things. Now remember, the speed was given by this new quantity s prime of t, which was just r prime of t like this. The unit tangent vector was defined as r prime of t over the length here. R prime of t magnitude. This could be interpreted as r prime of t over scalar s prime of t. R prime of t is simply just s prime of t times this unit vector. So this tells me something about a size, which is essentially the speed, and then this just tells me a direction. Now remember, r prime of t was the velocity. So I now have another way to interpret velocity. When I am moving along a curve, we've already discussed that here is your location r of t. The velocity was always tangent to the curve. Well, there's the v of t. This is just another way to see it. The size of the velocity here, you could think of this s prime of t as the linear velocity, the velocity in a straight line or tangential direction, and this just tells us the direction. The acceleration is the derivative of the velocity, and that means it's the derivative of this expression that I just calculated, s prime of t times the unit tangent vector. Remember, the unit tangent vector changes depending on where I am on the curve. I've got to use the product rule, and I'll get s double prime of t times this t plus s prime of t times the derivative of that unit tangent vector. Well, remember from the previous video, this was related to the unit normal vector. The unit normal vector was the derivative of unit tangent over its length. And because of that, we can reorganize this expression. So acceleration is going to have an s double prime of t in this unit tangent direction, plus I will now have an s prime of t magnitude of the unit tangent vector in the normal direction. So I don't want you to get too bogged down by all of this, but the point here is the following. Acceleration has some tangential component because we can see that it's going in the tangent direction, and then it's got some normal component. It's going perpendicular. So what this is telling me is that motion along any curve produces an acceleration vector that's in a plane. The acceleration vector is some amount in the tangent direction and some amount in the normal direction. And remember, we've already discussed that those two vectors are always orthogonal to each other. So if I have some point here, there's my r of t, the unit tangent vector pointing like this, and then I have the unit normal vector pointing orthogonal to it. Those two will create a plane at any point along the curve, and the acceleration vector is some combination of them, so it lives somewhere in that plane. We've already shown from above here, this tangential acceleration is s double prime of t. This is what's called the linear or the straight line acceleration. This is the part of acceleration that always goes in the tangent direction, straight ahead. This other part, this we need another interpretation of. So we're going to introduce another new idea, something called curvature. So curvature is a number that tells how much the curve changes direction as we walk along the curve. And so if I give you a curve, in this first case, which is just a line, the unit tangent vector is never changing. It's always pointing in the same direction. We are going to say there is no curvature. There is no bend to the curve. As I walk along this curve, you can see that the unit tangent vector does change, but it doesn't change very much as I keep moving along the curve. So as I increase the distance along the curve, there isn't a lot of change. So in this particular case, I would say that the curvature is small. But in this final case here, you can see that the unit tangent vector changes its direction a lot as I move along the curve. So as I start moving this way, there's a lot of curvature change. And so we would say that the number for the curvature here is large. So mathematically, we would define the curvature as the size of the rate of change of the unit tangent vector with respect to arc length along the curve. It's always a number that's greater than or equal to 0. By the chain rule, if I'm given a unit tangent vector that has this arc length parameterization, if I wanted to take the derivative of it, I would have t prime of s vector times s prime of t, which is just a scalar. So that means then that this derivative with respect to s is simply going to be the derivative with respect to t over s prime of t. And that means then that the curvature, which is the magnitude of this vector, is going to be the magnitude of this over s prime of t. And remember that s prime of t is always greater than or equal to 0. If we go back to that normal acceleration, we had an s prime of t times a magnitude of that unit tangent vector. Well, from above, this is going to be now an s prime of t that was there before times a second s prime of t times this curvature. So that means that the acceleration vector, it's got this s prime squared times kappa in the normal direction. So acceleration depends on how curvy the curve is. The more it curves, the more you're going to feel this perpendicular or centripetal acceleration.